zones are calling. You have more fittings and more dampers and more restrictions and so forth. And then in addition, because of those extra dampers and ducts, systems are more prone to construction failure, construction errors. These are very common, and because the duct system's bigger, you get bigger duct losses as well. So so just so you know, we've seen these things. This is a typical California kind of installation where you got the furnace here and the air conditioning system. It's kind of a distorted picture, but that's what's operating right here. There's the flue from the furnace, and you have ducts running around in this hot attic, and this duct right here is the bypass duct for the system. So it runs from the supply plenum over here to the return, and cold air comes from the supply and goes over here and goes back into the return, goes around and around. Here's another example in one of the houses we surveyed where there's this 16-inch metal duct here that goes from the return supply over here to the return over here. And you can see the arm here of the gravity damper that's supposed to open and close when the pressure in the duct system change so that the air can go back around in the bypass. Okay, so one of the things we wanted to acknowledge was the comments from some stakeholders based on our case presentations. The Air Conditioning Contractors of America and the American Heating and Refrigeration Institute, AHRI, both commented that they want to maintain the current credit for zone systems, and have argued that in some cases there's energy savings, and they want to maintain the use of the bypass duct. There's been some research presented on dampered multi-zone systems that two cases of, well, these are two papers. I think they're related to the, maybe to the same experiments that were done at the National Association of Home Builders Research Center, sponsored by NAHB and Carrier. You know, we've looked at those studies, and there's some interesting conclusions in there. One is quoted here. It says that studies have demonstrated that a multi-zone system will use more energy than a central thermostat system when a constant set point is used. And a 35% increase was documented as a direct result of multi-zone system being more responsive to the cooling needs of the entire house. So, you know, the research indicates that, at least in some cases, you put a multi-zone system in and the energy use goes up. There's an ASHRAE paper which says that zoning with no thermostat set up use more electricity for cooling than the system in a central configuration with no thermostat set point scheduling. And again, part of the reason is that you're getting better temperature control, and the unit is responding to the loads in the house better and using more energy to do that. So one of the things we attempted to do as part of this project was we made a model of a zoned air conditioning system, the kind of characteristics that we find in California houses, and tried to look at how much impact the zoning system would have on the efficiency. This is a theoretical model that we're showing here. And what's plotted on here is the results from this model. And on the left-hand side, what we have is the net sensible EER, and it's in a percentage terms, and it's relative to the rated value at 350 CFM per ton and no bypass. So this is just saying what's the relative performance of this system compared to its rating. Across the bottom, we have the CFM of air delivered to the conditioned space, and again, relative to the rated values at 350 CFM per ton. And the the various lines here show the combination of different percentages of bypass and of total system airflow to the zone. So up here at the upper right-hand corner, where we have no percent of air that goes through the bypass ducts, we have 100% airflow to the zone, and we have, at that point, we get 100% of the rated EER. So this is what the nominal system would do is right here. So if you take that line with no bypass and just follow it across here, what it's saying is that if you reduce the airflow through the system by just putting in more restriction or turning the fan down or whatever it is to get the airflow to be less than, by the time you get down to 50% airflow, which is the 175 CFM per ton, then you are at about 83% of the nominal EER. So the system efficiency is 17% lower than rated when you cut the airflow down. And then these additional lines here are looking at the combined effect of that plus different percentages of air that goes through the bypass duct. So for example, this line down here is 50% of the air is going through the bypass duct, and the total airflow to the zone is, so at 50% and 50%, you're now down at efficiency is 77% of what you would expect for the nominal system at its rating. And we're doing this in terms of sensible EER, which is, we think makes sense in California climates where we're not really all that interested in dehumidifying most of the time, and we're really looking for big cooling capacity when it's very hot outside and typically dry. So that's the reason for sensible EER. So this is what the theoretical model, and this model is derived from standard air conditioning manufacturers' extended data tables. You can look for most residential equipment, and you'll find the manufacturers supply the data that you would need. And we use to plot this result. So the other thing we did is we went out and measured the detailed operation of zone systems in 3 houses that we selected from those that we surveyed in that field survey. Each one of these houses, we spent a whole day with a crew of people and measured the net sensible EER of the zone systems based on measuring, it's the tons at the register approach. You measure the airflow and temperature of the air at each supply register and the airflow and temperature of the air at the return register, and you can calculate how much cooling was delivered to the space. In this case, we're talking sensible cooling. And then we manipulated the controls in the systems manually to achieve different levels of bypass and different levels of CFM, and just to see what the impact would be on our net sensible EER number here. Again, the same terms, it's percentage of the nominal, and down at the bottom is the percentage of the CFM delivered to the conditioned space. And you can see that when you're up here at the 100% airflow to the space, we're in the neighborhood of 100% of the nominal capacity. The dark blue line here is field study house number 3. The gold line is field study house number 2, and the green one is field study house number 1. So we actually did this in 3 different houses, these 3 houses. And so what you see is basically similar to what we showed in the last graph, that as you reduce the amount of airflow that goes to the conditioned zones and increase the bypass, then the EER goes down. And this is at 27% bypass, this is at 45%, this is at 39%. It depends on the details depend on the system. And, there's lots of interactions between things like how leaky the ducts are and where they're located. And are you running more air through the ducts in the attic that have the big leaks or not? These are the systems as found in the field that are, it's only 3 houses, but the results all agree with each other pretty well. So if it's interesting that if you plot our theoretical model derived from the air conditioning manufacturer's data over the top of this field data, the field data actually shows that the situation is worse than what the manufacturers would have, data would have indicated. The percentage loss in sensible ER is actually bigger. Part of that is because, we think that part of that is because the manufacturer's data that we're using here is extrapolated down at these low levels, and they don't actually, they don't spend a lot of time testing because they don't really want people to be operating down here anyway. So and plus we're talking about real systems installed in buildings where there are duct losses and so forth, and that's not included in the manufacturer's data. So there's more things operating here than there are in the theoretical model. One of the interesting things that we discovered recently is there's a Air Conditioning Contractors of America, ACA, has a new standard that's been out for public review called Manual ZR. There's a reference down here at the bottom. It's a standard for how to do zoned air conditioning systems for residential low-rise buildings. And we looked at their drafts, which is, as I said, has been out for public review, and so it's not a final document. And there's a set of data in there that shows what ACA thinks you should expect from a zone system where you have certain levels of bypass and certain levels of airflow. And you know, their curve, which is the blue line here, basically matches the field data from we're comparing it to field study house number 2 here, just for example, but it's basically the same pattern. So the stuff we're finding in the field seems to be what you know, the people who know about zone systems would expect you to find. So the question about why are these bypasses so bad? And kind of as a thought exercise, if you imagine this system here, where you have your furnace and your cooling coil and your fan, and you're taking air and you're blowing it out, and all the air is going through the bypass and back into the return duct, and no air is getting delivered anywhere. So what happens then is that if you're in heating mode, the temperature, you know, very quickly goes up to the outlet temperature of your furnace, and at that point you can't add any more heat to the air. Well, actually, what will happen is it'll start running on the safety switch and turning off the gas valve. But in cooling, the temperature drops down to the, you know, keeps going down colder, colder, colder until again you end up with the system going off on safety controls. But it gets harder and harder and harder to provide cooling when the air coming back to the system is actually at the temperature you're supposed to be making it with the air conditioning. So this, you know, this is what's going on with the bypass.